Okay, welcome back. So today we're going to be actually diving into some of these statistical inference methods, and we're going to start looking at confidence intervals, what those are all about. Okay, so we know what statistical inference is, right? We're using a sample to figure something out about the population that it came from. All right, the most basic form of that we've already talked about is point estimation. All right, we saw a little bit about point estimation. And we're going to build off that to talk about today about confidence intervals. Hypothesis tests will come later. That is another form of statistical inference that can answer a different question than what we'll be asking today. Alright, so remember what we're looking at so far is we're using x bar, the sample mean, to try to estimate the population mean. Right, so x bar, we know, is a good, unbiased point estimate of mu. Okay, so we know about this idea of point estimation, right? Using one specific statistic to estimate a specific parameter, and that it usually does pretty good, right? But it's not going to always be perfect, right? Especially we know that for smaller sample sizes, our process there isn't as precise. Okay, so since in most now we've simulated in the past repeatedly sampling and seeing what point estimation looks like if we repeatedly sample, right? But in practice, we really only get to take one sample, and we kind of have to hope that sample's a good one and just go with it, right? So the question is, how can we just use a single sample and guarantee that that sample is producing results that are good estimates, right? Well, we know about the variability, the sampling distribution, and all this stuff about x bar, right? So if we can use what we know about the sampling distribution of x bar, what we know about its variability, right, we'll use that point estimate and we'll supplement the point estimate to create what we call a confidence interval. All right, remember our goal in this specific case using x bar to estimate mu, right? We know all about the central limit theorem, right? What it tells us about x bar sampling distribution, x bar's variability. Okay, so we take a point estimate, we supplement it, we build in a little bit of wiggle room here. Okay, so we take our point estimate and add and subtract what we call our margin of error. Okay, the point estimate minus the margin of error, the point estimate plus the margin of error will give us a range or an interval of possible values. Right? And this interval will also come with what we call a confidence level. Right? Because we're starting to figure out in statistics, we're never 100% sure about our answer. Right? So every answer with these statistical inference techniques we'll see comes with some sort of indication of its variability as well. All right, so say our goal is we're trying to estimate the average height of all males in Virginia, right? So obviously we couldn't get to every single person in the state, measure them. We couldn't perform a census, right? So we have to take a sample. So let's say we take a sample of size 36. All right, now usually things with humans, heights, weights, stuff like that, we know can typically be assumed they're normally distributed, but we don't know that. Okay, so even if we can't assume the population that we're sampling from is normal, sample size 36, big enough, we can assume central limit theorem holds. So we know in this case we'll be using our z distribution, right, the standard normal. So we take this sample of size 36, but other than this sample, we don't have any information about the population we're sampling. Right? Now, in order to use z to use the central limit theorem, we have to go under the assumption that we know the population standard deviation, that we know sigma. So let's just choose an arbitrary sigma 3. Okay, so we'll assume we can say that our central limit theorem holds here. Alright, so we know about the sampling distribution of x bar, right, but we don't necessarily know what mu is. We don't know what our population mean is. We're using x bar to estimate it. So say this is the sample that I take, and I get a sample mean of 68.5. All right, now that 68.5 we know should be, in most cases, pretty accurate estimate of mu, but it may not be perfect. So theoretically, the sampling distribution of x bar looks like this. It's normal, centered at mu, with a standard error of sigma over root n, sigma here being 3, n being 36. That gives us a standard error of 0.5. Now the question is, that value of x bar that I just observed, where exactly does it fall in that distribution? Right? Because we don't know what mu is. So x bar of 68.5 could have been a little bit less than mu, could have been a little more, a lot less, a lot more. Right? Point is, we know what the distribution theoretically should look like, but since we don't know mu, we don't know exactly where our observed value falls on this distribution. Okay, but what else do we know about the normal distribution? Well, one of the first things that we talked about, and one of the first things that should pop into our mind when we hear normal distribution, well, what about the empirical rule? Okay, so our empirical rule, the 68, 95, 99.7 deal. All right, well, let's just use 95. If we go about 2 standard deviations away from the mean, we should see about 95% of our area there. All right, so remember, our distribution was normal, centered at mu, standard error 0.5. So if I say 2 times 0.5, right, which is 1, and I go out, that area should be about 95%. All right, so take back into account the 68.5, go out those 2 standard deviations, so 68.5 plus 2 times 0.5, remember 0.5 was our standard error, 68.5 minus 2 times 0.5, that's 1. So if I make this interval from 67.5 to 69.5, even if 68.5 is a little bit less than the actual value of mu there in the center, mu is still included in this interval. Or if 68.5 is a little bit more, mu is still included in this interval. If it's a little bit less, it's still included in the interval. Now there is a chance that I get some sort of weird value of x bar, and it's more than 2 standard deviations away, and the mu that I was looking for is not included in that interval. So remember, that is a possibility. All right, but for the most part, if I construct this interval in this way, go out 2 standard deviations from x bar, I ought to capture, most of the time, that value of mu that I'm looking for. All right, this is the idea of, in this case, since we went out 2 standard deviations, this is the idea of what we would call a 95% confidence interval. So we're about 95% sure that this interval captures that parameter we were looking for. In this case, the true mean height. All right, so maybe you're seeing now what we mean by we're supplementing x bar, this point estimate, with what we know about its sampling distribution, about its variability. All right, so let's think about the formula that we just used to construct this interval. Well, basically what we did was we said x bar plus or minus 2 times the standard error, where the standard error is made up of sigma over the square root of n. Right, now that 2, where did that come from? It was sort of arbitrary, and it came from what we knew about the empirical rule. But if we want to be more precise here, remember what our empirical rule says. So let's try to visualize this again. Remember what our empirical rule says? About 95% within 2 standard deviations. About 68 within 1 standard deviation. We could have done this whole same demonstration instead of 95. We could have done it with 68. Right? About 99.7 within 3 standard deviations. Our empirical rule isn't exact. It isn't precise. So what if I want to say, not I'm about 95% sure, what if I want to say I'm exactly 95% sure? Well, I won't go out 2 standard deviations on the standard normal distribution to be exactly 95% sure. I'll go out 1.96 standard deviations. Okay, so how do we find that number 1.96? Well, if there's 95% in the middle, what's left over on the outside? 5%, right? So, because we know 100 total minus 95, 5% left. Okay. All right, but that 5%, I got to divide that over two areas. So 5% divided by 2, that gives me 2.5%. Right? So if I go to my table, because we're working with a standard normal distribution, if I go to my z-table here, then that 2.5% I was looking for, so remember we kind of have to estimate this. We may or may not have exactly 2.5%. Convert 2.5% to a decimal. Here we go, 0.025. Alright, so right there, 2.5%, I go to 1.96. Remember how our z-table is set up? That's 1.96, and there we go. So that is how we find, and that's how we find this exact value of 1.96, right? Rather than just using an approximate one of 2. Alright, so think about what we just did. That number, 1.96, corresponded to 95%, right? And the calculation that we did, 68.5 plus or minus 1.96, this is called our critical value times the standard error. Right, we did this math. Our standard error is 0.5. Now when you see confidence intervals in practice, I've got 3 different ways that they're oftentimes presented here. Right, sometimes your confidence interval is just presented like this, your point estimate plus or minus the margin of error. Simple, quick, easy way of presenting a confidence interval. Sometimes it's presented like this, your lower limit and your upper limit. The lower limit is the point estimate minus the margin of error. Your upper limit is the point estimate plus your margin of error. Sometimes it might be listed this third way. And I like this third way because it kind of helps us keep in mind, well, what was the point of this anyways? Right? We're trying to estimate mu. Okay, so this is telling us mu, right, is somewhere on this interval. We're pretty sure, in fact 95% sure, right, that we've captured mu with this interval. Alright, well maybe you were thinking, well 95% seems kind of arbitrary. Okay, that's fine. What if we want to be, and maybe you're not happy with 95%. What if you want to be 99% confident? Okay, so what do we do there? Well, similar idea. There's 99% in the middle, 1% left over. Right, 1% left over total on the outside. Divide that 1% in half, that's 0.5% in either of these areas. So if you go to your z-table, if you look up this value, 0.005, or the closest thing to it, you'll find 2.575. Alright? Now these values, 95, 99, 90, these are critical values that we use a lot. Okay, but let's just try to generalize that, because in practice you guys will use this enough that you'll probably memorize the z critical values associated with 90, 95, 99. Right? But in case we see some kind of weird confidence level, like find an 88% confidence interval or something like that, for whatever reason, we want to know how to generalize this process. Alright, so the idea was we took our confidence level, right, that was 95, 99, 90, whatever it might be, we said 1 minus that confidence level to give us what was left over outside. That area that's left over outside is usually denoted by this symbol alpha. Right? We'll revisit alpha in the future. Okay, then what we did, we took that alpha, we divided it by 2 because there were 2 areas outside, right? And then that's what we looked up in the table. So your critical value technically should be denoted like this, your z of alpha over 2. But I've also seen it like this, zc or z star. Now Z star is a quick, easy way of doing it. So lots of times that's what how you'll see it written in my notes, Z star. All right, so say we want to find the critical value for a 92% confidence interval. So first, we're going to want to draw our picture, right? I think that kind of helps us keep everything straight from the beginning, just drawing our picture there. All right, we then use this idea, 0.92, 1 minus 0.92 leaves us 0.08, divide by 2, 0.04. All right, and finally, look that up in the Z table. All right, with that 0.04, let's see what that shows us in our Z table. So I've got 0.0401, right? That's pretty darn close. It's not exact, but whenever we're dealing with these probabilities in the Z table, we just get what's close. So that's 1.75. All right, 1.75 looks pretty good. Now, if I want to check myself in Excel, okay, I can go to norm. Remember these norm.s functions when we're dealing with the standard normal distribution? So we said 92%, 1 minus 0.92, 0.08, left us with 0.04. Put that in. And if we needed a more exact answer, there we go. Now to more decimal places than what you got from the table. So, in general, so let's again try to generalize this process. What we did was we took our point estimate, built in that margin of error, where our margin of error was made up of the critical value. So this whole thing here makes up our margin of error. All right. So our margin of error is your critical value times the standard error. We used what we knew about the sampling distribution of x bar here, which was our point estimate. We took that and we said, okay, it's normal. So I can use a z critical value. My standard error is this. So I plug in that quantity. That's how we built this confidence interval formula. So think about the interval we created earlier. Right, it looked like this, our 95% interval. And really anybody can just plug into a formula. I mean, that's not hard. The hard part is just making sure I use the right critical value. Other than that, it's pretty much plug and chug. Right, but what's more important to us is, okay, here's this interval, here's these numbers. What does that mean? Well, what was the objective? What were we trying to do? We were trying to use that sample to estimate the value of our parameter of interest. Our parameter of interest here was the mean height of all adult males in Virginia. Okay, so using this information, we can say that we're 95% confident, right? We know that because we use that critical value 1.96, that this interval we created captures our parameter of interest. All right, so notice that wording there. So I want to expand on the interpretation of these things a little bit. The interpretation has everything to do with the objective of this interval. Right? Remember the interval, it either does its job correctly or not. Right? It captures it, yes, or no, it doesn't capture it. Right? Just make sure when you're interpreting this, you're talking about your interval, not the parameter that you're looking for. Right? When I associate this confidence level, the confidence level is associated with our interval, not the parameter. The parameter is a fixed value, right? It's not changing. There's a 100% chance that that parameter is what it is, right? We're trying to catch it. We're trying to capture it. Okay, so when we talk about this confidence level, we want to associate that confidence level with the interval we're creating, right? Not the parameter itself. So a general interpretation would be, well, whatever percent confident that this interval we created captures our parameter we were looking for. All right, I bring that up because lots of times these things are interpreted incorrectly. You might say something like, there's a 95% chance that this interval I created includes my parameter of interest. or there's a 95% chance that this parameter is between these two values, the endpoints of that interval. No, there's a 100% chance that that parameter is what it is. Right? If you talk about it like that, that's implying that this parameter is some sort of moving target. It's some sort of changing thing. That's not true. What's changing is the sample that we take, right? Therefore, the statistic that we calculate could potentially change, right? Which gives us a different estimate. The parameter itself is not changing. Okay, so we want to be careful about this interpretation. Now, one more way we can interpret this is to think about what would happen. So here we're going to go back to kind of simulation mindset. What would happen if we created a whole bunch of confidence intervals all under the same conditions? So kind of like we've done before, we're gonna visualize here making 195% confidence intervals, right, for a given mean value, say mu equal to 16. We've used that before from a previous example. All right, and under all the exact same conditions, I simulated sampling 100 different samples of the same sample size and created 195% intervals from that. Now keep in mind the job of an interval. The job of a confidence interval is to either capture that parameter of interest or not. So I did it 100 times. Here's the first 20. Out of these first 20, so here's our mean, this red line in the middle. Out of our first 20, looks like one did not do its job, the rest did. Our next 20, okay, here's one that didn't do its job, the rest did. Our next 20, from 40 to 60, all of them did their job correctly. Right? Our next 20, one missed there. And our last 20, we had another one miss. Okay, so in simulating this, it turned out that 4 of those 100, which is actually 96%, didn't capture our parameter of interest that we were looking for. Okay, but that's, even though here it was 96%, if I was able to do this 1,000, a million more times, we would actually see that 95% of these tend to capture the parameter of interest. All right, so thanks for tuning in, and we'll look at an example of this in the future.